Hello, and welcome to another wonderful episode of the New York City Category Theory Seminar. And today we have Sam McCrosson, and he's going to talk about exoderm. Sorry, I didn't write it down. And he's going to tell us what he's going to talk about in 1 second. And take it away, Sam, please.
Right on. Thank you very much. I'm very excited to be here. That's right. The topic of the day is exodromy or exodromy. It's a made-up word. I've heard it pronounced both ways, so whichever you kind of prefer. Um, but yeah, it's a ultimately I think of it as a categorical result, especially when you consider it holds in all these different contexts. There's a version of it for topoi. There's a version of it for schemes. There's all sorts of versions of it. I'm going to present just the sort of most austere, topologically motivated version using just topological spaces in one categories. And ultimately, well, it's the equivalence you see on the screen before you. We're going to be talking about how functors on this object called the exit path category here are going to be equivalent to what we're going to call constructible sheaves on the underlying space. This is not original work. It ultimately goes back to the 70s and 80s with Robert MacPherson. And then it's been generalized in a whole bunch of directions since then. So more recently by Peter Hain, Clark Barwick, and Saul Glasman, as well as Justin Curry and Amit Patel at CSU. And I've seen a bunch of versions of this. So I'm just going to sort of present the topologically motivated side of the story, but it holds in a whole bunch of different contexts.
Hold on, Sam. You forgot the most important thing.
Oh, right.
Right. So again, where you were born, where you got your undergraduate degree, where you got your PhD, and where you are now.
Yeah. So I was born in Lancaster, California, but I was raised my pretty much whole childhood near Boulder, Colorado. I went to undergraduate at Colorado State University in Fort Collins. I got my master's from Montana State University in Bozeman, Montana. I don't have my PhD yet. I'm still working, or not working towards that actively. I'm currently teaching as an adjunct at the University of St. Thomas, but definitely interested in finishing up that PhD. Yeah.
Perfect. Very nice. Thank you. So you're living now in where?
Minneapolis, Minnesota. That's where the University of St. Thomas is.
Perfect. Okay, go.
Yeah. Thank you for the reminder. Yeah, so before I even jump into anything, I do want to thank some people who got me here. Got to thank my graduate advisor, David Ayala. He showed me this stuff in the first instance. Ray Puzio, who I believe is in the audience. He was sort of the connection here that got me talking in this seminar. Nosen for organizing everything. CUNY for being our host institution of the night. And all of you in the audience, thanks for coming out in the evening to check out what I think is a really interesting and beautiful subject. So let's start with a sort of the most simple place we can start. Let's think about taking the square root of a real number. So square roots famously are not a function, but we can still write down the graph of the square root as the set of all points in the plane such that y squared equals x. And if we sort of graph this thing, it makes this kind of shape where we have the positive square root and the negative square root, right? Okay, fine, but there's a lot that this picture already leaves to be desired. What do you do with negative numbers? And so, well, let's think about if you have complex inputs to your square root function. We can mimic the same formula for the graph. So let's say it's going to be all points in C2. Let's remove the origin for now. We'll come back to this in a second, but just for now, let's remove the origin because you notice the origin is a little different than the rest of the numbers. The origin only has one root. Everything else has two. So if we write out just this sort of set in the two copies of C, what we get is a surface, a Riemann surface. I'll see if I can draw it here. That it's going to be a rough sketch, but it's essentially a sort of hourglass shape that's twisty. Like the bottom lobes of the hourglass fold into the top lobes. I'll make that precise as we sort of explore this thing and look at paths that you can walk around in this thing. But the main thing I want to observe right off the bat is call this RS square root for the Riemann surface of the square root. The first thing I want to observe is that there's a natural projection from this thing to the punctured complex plane, where you take a pair z comma w. Remember, w is one of the potential square roots. And just forget about w. Just map it to the first coordinate z. So this is a projection sort of operation. Got c downstairs, and we can call this map p for projection. The first thing I want to observe about this setup is that if we have a point, maybe 1 in the complex plane, it will have 2 preimages upstairs, right? There should be the positive square root and the negative square root, since we're dealing with just a real number, right? And we can make a sort of further observation for any point in the complex plane downstairs. So for any point z in C without 0, you can find a little neighborhood about that point z. Say it is an open neighborhood in C less 0, such that maybe I can draw this as I describe it. Any point in the complex plane downstairs sort of has a neighborhood that if we look at it, if we look at the preimages of that neighborhood, it should just look like 2 copies of that neighborhood upstairs. And so we can organize this by saying the preimage of uz should look like just uz itself 2 times. I'll say crossed with 2 element set top and bottom. And furthermore, this homeomorphism commutes with the projection, so that if you project off of the actual preimage, or if you project off of uz crossed with top and bottom, you should get the same thing. And so this sort of situation, if you've taken a course in algebraic topology, you probably recognize this as a covering space. So the Riemann surface of the square root lives over the punctured complex plane as a covering space. So what does that mean in, I don't know, useful terms, or what are some consequences of this? Well, remember, covering spaces are great because they satisfy the path lifting property. The path lifting property says if we have a path, which I'll represent as, we take the unit interval.
So, Sam, one quick question. How do I think of that third leaf on your covering space? In other words, if you want to say 1 is positive, what the hell is the third thing?
It's really, we really have 2 lobes. There's really like a top lobe and a bottom lobe, but the 2 lobes twist into each other. So the fact that I drew sort of what looks like 3 lobes is supposed to indicate that the top is like twisting into the bottom as we go around. And if you chase it around, you twist from top into bottom.
Okay.
Yeah,
okay. So can it be visualized? I mean, it's part of a 4-dimensional thing, and it's
right. Not perfectly. It's like a Klein bottle where you can't put it in 3 space without it intersecting itself.
Yeah,
okay.
There's a simple trick you can do with just a paper where you twist it around, where you basically see it if you drop 1 dimension.
Right.
Okay. Thank you.
And so let's say we imagine a path in the space downstairs. Let's use a particularly nice one. Let's just say our input in the interval goes to e to the 2 pi it. So we walk in a circle. So this would look like just walking in a circle around the origin in the complex plane. The path lifting property says that if we choose an initial lift of our base point for the loop, so maybe I can recall we've got 1, -1, and we've got 1, 1. The path lifting property says if we choose an initial lift for the base point, which we might write diagrammatically as saying we select out something that gets sent to the start of this interval, and let's say we pick out 1, 1 upstairs as the initial lift. So the loop, when we lift it, it will start here. The path lifting property says we get this diagonal lift, gamma hat. And we actually have a formula for gamma hat. If you're embracing the fact that we're working with the complex plane, we can write down a sort of formula for the square root. So we could say gamma hat of t is going to equal, it needs to be the same as the first coordinate, z, will have to be what it projects down to downstairs. So that'll be e to the 2 pi it. And then the square root, you could get that by halving the angle. So that'd just be e to the pi it, right? And since the angle for the square root increases at half the rate of the angle for the loop that we're walking around, when we lift this loop downstairs, we see that it lifts not to a loop upstairs, but to a sort of path that walks from the initial lift to the other possible pre-image of our base point. And so this phenomenon that loops lift to paths, this is what we call monodromy in sort of the classic topological setting. So exodromy, what I've come to talk about, is going to generalize this. But let's just sort of take a second to really drill down on this monodromy phenomenon and see how we write this as an equivalence of categories. Because there are various categories going on, sort of, I don't know, they're in the air. So one thing you could note is that this works for all paths, not just loops based at a point. So maybe I can write this as the Riemann surface of the square root projecting to the complex plane less 0 determines a functor, actually, I'll call it f, whose source category is going to be the fundamental groupoid of the complex plane. Just to remember what that guy is, we have that for any space X, we can sort of organize all the homotopical path information by saying we've got a category, we call it pi1x, the fundamental groupoid of X. The dots of our category, the objects, are just going to be the set X itself. And then if you're interested in a Hom from X to Y, so you have 2 points, X and Y, in the space, this is going to be the set of paths from 0, 1 into X that sends 0 to our point X, 1 to our point Y, and then we want to only consider these up to homotopy. So the fundamental groupoid organizes points in the space and homotopy classes of paths among those points. And so our Riemann surface of the square root projecting onto the punctured complex plane can be thought of as a functor on this thing, valued in sets that, what does it do to a path gamma from X to Y? It's going to send the point X to the fiber over X. The point Y will get sent to the fiber over Y. And then using this path lifting property, we get a map gamma bar from the fiber over X to the fiber over Y, that essentially you choose an initial lift of your path gamma, you choose a starting point for the lift, and then you just take it where it leads you. You follow the lifted path gamma hat, and that should end at some point in the fiber of Y. And so your initial lift in the fiber of X will just get mapped to that final point in the fiber of Y that the path lifts to. And just to emphasize, I don't know, got to draw a diagram sort of, in this instance, what does the fundamental groupoid look like? We only have, if I draw a skeleton, there's only one isomorphism class of points since the punctured complex plane is path connected, but there will be an integer's worth of automorphisms of that point. And those automorphisms will compose just like the integers add. So it's sort of organizing the fundamental group of the punctured complex plane, but we're thinking of it more in categorical terms. So this setup where you have what's ultimately on the left, a covering space, and it induces a functor on the fundamental groupoid of the base, valued in sets. This generalizes. I don't have to use the punctured complex plane downstairs. We could say this is sort of the first statement of monodromy. For a nice space X, and by nice, I just mean it satisfies some appropriate point set conditions. I think it has to be locally path connected and semi-locally simply connected. If we have a nice space X, we get this, oops.
Right, so it sounds like the usual conditions needed to have even something like a fundamental group makes sense.
Right, that's right. And so we get this functor that goes from covering spaces over X to functors on the fundamental groupoid of X, valued in sets. The functors are valued in sets. And this turns out, using the same sort of setup we saw in the last slide, where you take the covering space, you look at the fibers over points in the base, as those are your sets that the functor spits out, and then paths between points in the base induce maps between fibers. This turns out to be an equivalence of categories. So that's sort of the first way that we could say this monodromy theorem using a little bit more categorical language.
Can I ask a question? Can you are you allowed to back up a little bit one time?
Yeah,
or?
absolutely.
Okay, so just why is it a groupoid? If you're looking at loops in C minus the origin, it should be groups, not groupoids. In other words, okay, so you understand the question. Go.
Yeah, so we could write this actually as sets with an action from the fundamental group of C less 0.
Right.
So you could say they're pi1 of C less 0 sets.
Right.
Just another equivalence of categories under the rug, where sets with an action from the fundamental groupoid are equivalent to just functors on the fundament, or sorry, I said sets with an action from the fundamental group are equivalent to functors on the fundamental groupoid. I like to use the fundamental groupoid because that is going to be a better match for when we generalize this story to exodromy. We'll see there's an object that plays the same role as the fundamental groupoid.
Okay, so it's a little bit unnatural because you are looking at loops downstairs, but you have a reason for it.
Yes, yes. Okay. And those loops will induce an action, right, on the fibers of the covering space. Yeah. Right. And so I agree. There is maybe a more natural way to write this down, but I'm embracing the fundament or functors on the fundamental groupoid version because that's what will, I don't know, we can sort of pattern match when we generalize.
Perfect. And the equivalence of categories. So clearly a lifting is not unique. So that's why it's an equivalence.
It will be unique to homotopy. And so if we only care about homotopy classes of loops or homotopy classes of paths, then this is, it's well defined, at least up to homotopy. And that's all we really need to get the action.
Right, but I mean, you might be able to take a quotient category of func, and then you'll get an isomorphism of categories or something like that. But the equivalence of categories comes from the fact that it's really not unique. That the lifting thing is not unique.
Yeah, you're saying. Like if we were to check that this is an equivalence, we'd want to show it's essentially surjective on objects. That's not to say it'll hit everything in the target category. And so, yeah, there's a choice if you're like going the other way of if I hand you a functor on the fundamental groupoid, there's maybe like a family of covering spaces you could build out of that, but they'll all be isomorphic to each other, right?
Right. Okay, good.
Yeah, so sorry, Sam, yeah. So the objects of coverings of X are, of course, covers of X, and the morphisms are, if I have a covering map like Y to X and then Z to X, it's just a diagram, right? Okay, yeah.
Yes, yeah, and so it'll be a map upstairs that makes the diagram commute.
Okay, yeah. Okay, so I see. So you can send a cover to its uh, fiber functor, as you said, right?
Yes. Yes.
Okay, yeah, thanks. Great.
And so this is just using covering spaces. These are like in the slice category over X, and functors on the fundamental groupoid. Points are very important all over this picture, right? We care about the fibers at X. We care about these paths that start and end at X and Y. We can organize all this information in a pointless way, emphasizing the open sets of the topological space, not the points of the space. And so consider this. We could have the Riemann surface of the square root projecting onto the punctured complex plane. And that will determine a functor, I'll also just call it F, that takes in open sets of the punctured complex plane, op, this is going to be contravariant functor, and spits out sets. And what's this doing? If we have an open set U contained in an open set V, which just recall this curly O of C less 0, we're organizing all of the open sets of C less 0 as a poset first, organized by set inclusion, and then we sort of think of that thing as a category. And so we can, for an open set, instead of thinking about the fiber over a point, we can think about all the sections over that open set. So I'll call this, I don't know, gamma P. Yeah, actually, perhaps I can name this functor gamma P. For sort of the sections of this map P. And so we can look at the sections of U, the sections of V. And so these are just continuous maps from the open set into the total space upstairs that commute with the projection. And if we have a section of V, a way of taking square roots in some larger open neighborhood, we can restrict that to sections of U, the smaller open set contained within. Here, actually, maybe I can slide this up a little because I want to observe that the sections of the open sets, gamma P of U, we're basically just talking about, yeah, maps from U into the total space that are, when followed by the projection, result in the identity. We really have, like I sort of drew previously, there's like a top lobe and a bottom lobe. There's two roots of any given complex number. And so this is going to essentially be maps from U into the set top and bottom for any open set U in the punctured complex plane, which, if you've seen this sort of setup before, where we're taking sections of a continuous map or something, you might be like, oh, this looks sheafy. This looks like a sheaf, right? And that's what I want to remark, is that this is a sheaf. And it's constant at top and bottom. So we have a constant sheaf at this two-element set, top and bottom. And so if you're familiar with sheaves, great. If you're not, they're important. So I'm going to spend just a second saying an brief overview of what's a sheaf, because they will be sort of a central character for the rest of this talk.
Hold on, before you change the thing. Somehow there is some type of action on the left on O of C minus slash, and this functor has to be somehow equivariant on that, and that's called deck transformations.
Does this functor need to be equivariant? I'm thinking if we're just assigning sections of various patches of the punctured complex plane downstairs, you would, maybe let me flip to a picture. Yeah. If this blue set is our open set U,
right,
we basically have to decide for each point in our open set U downstairs, we have to match it to a corresponding point in one of two preimages upstairs, right?
Right.
And if you could imagine having a family of open sets that sort of circle around the origin here. You'd have two choices of how to lift, or two possible sections of each of those open sets, right?
Right.
But by the time you circle back around to where you started, you've moved sort of upstairs. These sets look like this, where, I don't know, maybe I'm sketching off the top of my head, so there might be some holes in this. But essentially what we're going to find is that if you have an open set that circles the origin, you're not going to have any continuous global or continuous sections of that open set, because by the time you come back to where you started downstairs, you're at a different value upstairs, and that sort of suggests a discontinuity. Does that make sense?
Right. Well, another way of saying is your gamma was only a pre-sheaf function,
Right.
or set, not a sheaf, which would have an extra condition that would prevent that.
I think it is a sheaf, because we need, in order for the sheaf condition says we can glue stuff together when they agree on overlaps. Here we would have different overlaps that do not agree. Like the overlap here might be matched to this. Wait, let me think about what I'm saying. We do get a sheaf. We do get a sheaf. Because we glue sections together locally, but they might not glue together into a global section. There are no global sections.
You don't have to. I mean, this is just. I'm having memories of algebraic topology too, when we talked about deck transformations, and
totally, yeah.
And at one point, I actually understood it, and so I thought this is where it would be. But
right. Well, and the group of deck transformations will be isomorphic to the deck transformations of the universal cover will be isomorphic to the fundamental group of the base, right?
Right.
So that's all definitely relevant to this story.
But it's not in this functor.
Yeah, I don't think it's present in this functor, right?
Okay. Okay, fine.
Just to briefly recap what a sheaf is, I wrote this out.
Sam, sorry. What do you mean that the sheaf is, the global sections sheaf is, the section sheaf is constant upstairs? Doesn't it take in values from downstairs? So how's it constant?
Oh, if I said constant upstairs, I may have misspoke. It's constant on open sets downstairs, meaning it doesn't spit out necessarily the same thing for every open set downstairs, but it always, whatever it spits out for open sets downstairs, it's always of this form, where it looks like maps from that open set into the two element set, top, bottom.
So that's what you mean by constant at the set containing top and bottom?
That's right. That's right.
Oh, okay. I was going to say, yeah. All right. Thanks. Yeah.
Yeah. Because naively, you would say, like, for every open set, let's just spit out the same set. And that will give you a pre-sheaf, but it turns out not to be a sheaf. You need to sheafify. And this is what you get when you sheafify. So.
Okay. I see. Thanks.
Yeah. So just in brief, I don't know, in broad strokes, a sheaf assigns data to open set. And it does so in a way that if you have data defined on large open sets and you have maybe some subsets contained in there, the data should restrict from the large open set to the subset. And if you have data on the subsets that agrees on overlaps, you can sort of piece those pieces of data together and glue them together into one big thing. So the classic example are continuous functions. If you have a continuous real valued function on a space and it's defined on some large patch, you can restrict that to any sub patch. And the pasting lemma from topology says if you have two continuous functions defined on two different patches, but they agree on the overlap, you can paste them together into one big continuous function on the union, right? So continuous functions are this way, holomorphic functions are this way, differentiable functions. Lots of classes of functions are this way, but you also, sheaves turn out to be totally ubiquitous. You see them cropping up in lots of different contexts, right? And so just a little bit of vocab. I wrote this out ahead of time because I didn't want to get bogged down on the vocab, right? But a sheaf F is called constant at S if anytime we plug in an open set to that sheaf, it spits out something that just looks like maps from that open set into S. Like I just sort of alluded to, this is the sheafification of the constant pre-sheaf at S. If you have an inclusion, so say you have some subspace A as a subspace of X, this will induce a restriction of sheaves. So you can sort of restrict the sheaf data over all of X to just focus on the subspace A. And for the rest of the talk, I'll write that as F restricted to A. And we say a sheaf is locally constant. Maybe it's not constant everywhere, but maybe there's an open cover of the space so that when we restrict to pieces of the open cover, it's constant. This only really comes up if X is a disconnected space. A locally constant sheaf on a connected space, I believe, would just be constant. So with this sheafy vocab, we can get another way of stating the monodromy theorem. So for a nice space X, we have that sections will define a functor from covering spaces over X to sheaves that are locally constant. So let's say LC on X. And the monodromy theorem, you could say it as this is also an equivalence of categories.
So now you've arrived at, the special case of what you had on the very first slide.
Right, right, or almost, because on the first slide, if I can, I'm not going to flip all over just real quick, but I'll summarize it here. We had functors on the fundamental groupoid of X. The sort of first part of the monodromy theorem was we saw those are the equivalent to covers, but now the second part says there's a further equivalence to locally constant sheaves on X. And so composing the two equivalences, we get what is reminiscent of the first slide, functors on...
Right here, but you did show us the first equivalence.
Right. Yeah, maybe I will actually flip back to that real quick. Oh, come on. Yeah, functors on, we'll see the exit path category that's going to take the place of the fundamental groupoid turn out to be constructible sheaves on the space. So very similar. We basically have a simplified version for the monodromy theorem right now. So this triple equivalence I would call monodromy. And it gives you sort of three perspectives on the same phenomenon. You've got covering spaces are the same as functors on the fundamental groupoid are the same as locally constant sheaves on X. So what happens, pretty much this whole story hung together because we've removed the origin when we were thinking about the Riemann surface of the square root living over the complex plane. What changes if we include the origin? Well, notice, now we just have the complex plane downstairs. So observe that the fundamental group of the complex plane, well, that's just, there's only one homotopy class of loops in the complex plane downstairs. So there's not really any interesting loops to act on the preimages of points upstairs. Yet we still have the weird phenomenon. We still have this phenomenon that if I walk around the origin in the complex plane downstairs, it should create a path between the preimages of my points upstairs, right? So we should still have that loops lift to paths in a sense, but we only have one class of loops downstairs. So how do we account for this? There's a fix to this situation where it seems like the same phenomenon is happening, but we don't have enough data to describe it. So the fix is going to be to stratify our space downstairs. And by stratify, I basically mean carve it up into different pieces that are related to each other, and then specify some behavior of how the pieces are allowed to interact.
I understand the fix. I just don't understand what the problem is, in the sense that the loop on the bottom can be shrunk to a point, and the path on the top, I don't know what happens to that.
Right.
Well,
right.
the point, the path on the top can't be shrunk.
Right.
Right. So if we only consider loops in the whole puncture complex plane, no conditions, this should be basically functors from a point into I don't know, sets.
But no, but the path on top can be shrunk to a point.
Not without moving the pre-images. Like these pre-images really are 1 and -1.
Oh, I see.
One.
Okay, I understand. Sorry. Okay, good.
So you're right. If they're not fixed, like we don't care about what those square roots are, then you could contract that down to a point. But if we want to interpolate between those two distinct square roots, there's no, if everything's null homotopic downstairs, there's no way we could get an interesting action upstairs.
Okay,
right?
So you're going to stratify upstairs or downstairs?
I'm going to stratify downstairs, and then we'll put some conditions on the paths, essentially.
So not in your after you do your stratification, not all paths can be collapsed to a point.
Right. That's the goal.
Okay, thank you.
Yeah. So in service of stratifying, there are a lot of different notions of what it means to stratify a space. I'm going to go with what I believe is the most general definition, or I've seen comparison tables. I think this one's the most general. So in service of that, just recall for a poset, P with some notion of less than or equals, we can turn this thing into a topological space by giving it the downward closed topology, sometimes called the, I think it's the Alexandrov topology. So we'll call the open sets of this space all the sets A that satisfy this condition. If P is an A and P is less than Q, then Q should also be an A. So in an example, if I draw bracket 3, this is 0 is less than, 1 is less than, 2 is less than 3. The open sets will be everything that's sort of downward closed, the down sets. So we always have the empty set, but then we'll have 3 by itself, because nothing's less than 3, or sorry, nothing's greater than 3. Yeah, right. We'll have 2, 3. If 2 is in there, then everything that's greater than 2 has to be in there. So 3 has to be in there. We'll have 1, 2, 3. And we'll have the whole thing 0, 1, 2, 3. Right. Or just another quick sketch of an example. If I draw a poset that's maybe not linearly ordered, but maybe it like forks at some point. So I'll call this 0, 1 plus, 1 minus, and 2. Then the open sets here, you always got the empty set, 2, 1 plus 2, 1 minus 2. You could take the union of those, so 1 plus, 1 minus 2, and then the whole thing, 0, 1 plus, 1 minus 2. Notice any open set that contains 0 must contain everything that's downstream of it. So 0, the open set that contains 0 necessarily contains 1 plus, 1 minus, and 2. Okay. So then we'll call a stratification of a space is, for space X, we call stratification of X is just a continuous map from X into a poset with the downward closed topology. We call preimages of points strata. So let's see a couple examples of this. So the stratification that's going to be relevant to the square root story, we're going to take the complex plane and stratify it by bracket 1. So bracket 1 is just 0 pointing at 1. And so we'll send the origin to 0 and everything else to 1. This will sort of, we could draw this as like the complex plane, but then the origin is somehow special. So we have what we might call the 0 stratum and the 1 stratum, because that's the preimage of 1 is everything except the origin. Preimage of 0 is just the origin. No problem that just the origin is a closed set, because just 0 is a closed set in the downward closed topology. So everything seems to be working, I think. As just another quick example to see just how these things look. Or I've got a good example on the next slide, so I might skip this extra one that I have in my notes here. Here's a great way to stratify the sphere. So let's say you have the sphere, the n sphere, and we can stratify it by bracket n. We'll break it into n+1 many strata. And the way we'll do this is we'll send a n+1 tuple of coordinates, thinking of the n sphere as the unit sphere in Rn+1. We'll send it a string of coordinates to the maximum index where xi is not 0. So if I want to draw stratification of S0 by bracket 0 is a point, S0 is 2 points, so I might label the 2 points of S0 as the 0 stratum. S1, we have the 2 points for the 0 stratum, and then all the coordinates on the circle that have a y coordinate not equal to 0 will form the 1 stratum of S1. Up one more dimension, if we have S2, we can have sort of 2 antipodal points as the 0 stratum. We'll have what might be like the equator as the 1 stratum. And then all the points whose z coordinate is not 0 become the 2 stratum. So I'll sort of glue on to that. The north and south hemisphere, call that the 2 stratum. And you can just sort of iteratively glue on the north and south hemispheres in higher dimensions and call that, in 3 dimensions, the next dimension up, we'd call sort of the northern and southern 3 hemispheres, the 3 stratum. And yeah, you can imagine just sort of carrying out this process as long as you like, right?
So it's another way of looking at how you build up your spheres by suspending them.
Right, right.
Yeah,
and
anytime you suspend something else, that becomes the next stratum.
Yes, or yeah. Okay, so this is just sort of examples of stratifications, how we're going to carve up stuff.
Yeah, your example felt like simplicial sets in some sense.
Yeah, I definitely see that. The thing it really makes me think of our cell complexes, where it seems like we're sort of iteratively gluing on these higher dimensional cells in a way, right?
Right.
So if you have a triangulation, basically the same thing.
Point is that, yeah, geometrically realizing, realizing a simplicial or a cell complex, naturally gives you stratification by just the skeletons of different dimensions.
Yes. So yeah, as you increase the dimension, the higher sort of skeletons or the cells of, the n+1 skeleton become the n+1 strata, if I'm understanding you right.
Yeah, but
exactly. That's all.
Okay.
Yeah,
But just how are you going to stratify C with the complex numbers?
So the stratification we'll be interested in for the square root story is going to be this one, where we have the origin as the 0 stratum and everything else as the 1 stratum.
Oh, so it's okay.
Right. And so how does this help sort of describe what's going on with this phenomenon where if I walk around the origin, it permutes my roots? Well, here's sort of an idea. We can only let paths traverse one way. Only let paths go one way along strata.
So they can go from bottom to up or top to down?
So there is a sort of duality here where from one perspective, it doesn't matter, but we'll embrace going up in strata. So if you start in the 0 stratum here, You can hang there for as long as you want, but as soon as you leave into the one stratum, you're not allowed to go back. And then you can swim around in the one stratum, but you're not allowed to touch the origin again. And so if we lifted a path like that, it might start at the origin here, exit maybe this way, and then come around. And so it will lift to a path that sort of goes between the preimages of a point of interest 1 in the complex plane.
Do you look at anything more interesting kind of posets than a line?
You can, absolutely. And this will hold in sort of startling generality. The example, I was just going for sort of the easiest to draw examples. And so those are usually stratified by bracket n, where you just have a sort of sequence of strata that move from lower into higher strata. But you could imagine stratifying in all sorts of different creative, nonlinear sort of poset ways. Okay, so there's a great, this idea that we only let paths go one way along strata. We can state that by talking about exiting paths. We're going to name these paths exiting paths. And so we'll say a path into a stratified space is exiting the lower strata if, as time increases, you only increase in strata. So the value of the path at time t1 is going to be less than or equal to the value of the path at time t2 as sort of measured by this stratification. And so maybe just as a sketch, if let's stratify the complex plane by bracket 1 again, but I'll do it where the closed unit ball around 0 gets sent to 0, and then everything else gets sent to 1. So if I drew this, we'd sort of have the 0 stratums just fattened up a little bit. It's like, here's the 0 stratum, here's the 1 stratum. And so we would have an exiting path is the kind that starts here and maybe swims out into the 1 stratum. So this would be exiting. But if you started in the 1 stratum or went into the 0 stratum, or maybe you start in the 0 stratum, swim around in the 1 stratum, and then come back to the 0 stratum, those are not exiting paths. And so just like we were able to organize points in the space and then paths among those points as the fundamental groupoid for the monodromy story, we're going to be able to organize points in the space and paths among them, now directed paths along strata, as this new object that I'm going to call the exit path category. So if we have a stratification x over p, the exit path category, exit p of x, has as objects just the points of x, but then a morphism from x to y will be a path in x from x to y such that gamma is exiting. So we only consider exiting paths, and then we consider only up to homotopy by exiting paths or by exit paths. So sort of stratified homotopy, you want a homotopy between paths that every path in the middle is itself an exit path. So this is going to essentially take the role of the fundamental groupoid in the stratified setting.
One question, because one way of setting up homotopy paths, say, it's a path in the space of paths. So do you wind up getting stratification on the space of paths and then say, well, it's an exit path between exit paths?
Right. Yeah, you just add the stipulation that everything's an exit path all over the place. And people have made this sort of more concrete. There are more concrete ways to think about this in terms of like elementary homotopies, and it's been laid out in various levels of detail. My favorite of this particular side of the story is a paper by Justin Curry, Amit Patel. perhaps I can.
Maybe Friday you can give me a reference to that or whatever.
Yeah, I'll post a reference in the chat right at the end. So if we were thinking about the exit path category for the sphere stratification that I showed earlier, for the zero stratum, we have two disconnected components. So I might draw that as just two dots in my exit path category, call this the zero stratum, top and bottom. For S1, we could have two dots again for the zero stratum. And now we have two disconnected components for the one stratum. So maybe I'll draw that as two more dots. And notice that if I start at, say, this left point, I can exit the zero stratum into the one stratum in either way. I can exit into the top half or the bottom half of the circle. And the same goes for the other dot. So we get this picture for the exit path category of the one sphere stratified in that way. For the two sphere, it looks very similar. I'll draw two dots for the zero stratum, two dots for the one stratum, two dots for the two stratum. And at each, if we sort of zoom in on the zero stratum, on this dot, you could exit into the one stratum in two different ways. If you zoomed in, on the one stratum, you can exit from the equator into the north or south hemisphere in two different ways. So we get this sort of Jacob's ladder looking diagram for the exit path category of the n sphere stratified in this way. And you can just keep adding, another row of two dots and four arrows leading to those two dots.
Sorry, how do we make the arrows for one? You're saying, like, I would expect there to be. Oh, I see. For each of the black dots, you have two ways to get to. Oh, never mind. I got it.
Right, and you might wonder, if I'm going from the zero stratum straight into the two stratum, can that be witnessed as just a composite of the arrows I've drawn? Do I have to draw more arrows? And the answer is it is a composite of, you can relate these things by homotopies of exiting paths. So really, this is a full skeleton that I've drawn with all.
Unlike your complex plane, this is more, one way it's more complicated is now, say your two stratum isn't no longer connected, like when you took away just the origin, you took the whole equator and made it disconnected.
Right. That's right. Okay, so we're almost to the punchline, and then I don't think I'll get to my last example, but that's all right. So if we draw the exit path category for the plane stratified by bracket 1, where we consider the origin as the zero stratum, and then everything else is the one stratum, we would get two dots for a skeleton of our exit path category, one dot for the zero stratum, and then one dot for the one stratum. There's really, any 2 points in the one stratum can be related by exit paths going both ways, so they're all isomorphic in a sense. So I'll just draw one dot for the one stratum. There's one way that you can exit from 0 into 1. If you imagine like exiting up versus exiting down, those can be related by a circle or a half circle's worth of exiting paths, right? So there's really only one way to exit from the zero stratum into the one stratum, but then once you're in the one stratum, you'll have an integer's many ways you can swim around, just counting the winding number of how many times you wound around the origin after that point. Compare this with the fundamental groupoid of the complex plane punctured. That we saw was just one dot with an integer's worth of arrows. So that kind of looks like the right half of our exit path diagram, right? The exit path category just has this little bit of extra information. And so the question is, if functors on the fundamental groupoid are the same as locally constant sheaves, or equivalent to locally constant sheaves, then what are functors on this new thing, the exit path category? Exit P of X, what are these equivalent to? And so the answer turns out to be what we're going to call constructible sheaves. for a stratified space, a sheaf on that space is going to be called P constructible with respect to the stratification, if the sheaf is locally constant when restricted to strata. Essentially, F restricted to the strata is a locally constant sheaf. So maybe it's not a locally constant sheaf everywhere. Maybe it changes sort of at the interface of these strata. But if you restrict to strata, it's a locally constant sheaf. And so, for example, our Riemann surface of the square root with the origin filled in over the complex plane, this will determine a sheaf F on the open sets of the complex plane. That what is this doing on open sets? It'll send us open set U to one of two things. If the open set is away from the origin, we just get what we had before, maps from U into top bottom. And so that's if 0 is not in U. And if 0 is in U, we're looking at sections or sort of continuous square roots around the origin. There are none of those since it's a branch point. You would have to go from taking one square root into two simultaneously, and there are no ways to do that as a continuous function. So this, if we consider sections of the projection of the Riemann surface of the square root, they organize not as a locally constant sheaf, but as one of these constructible sheaves. And the punchline, just about at time, but the punchline is that if we have a stratified space and we need to make an assumption, the stratified space has to be what we call conical. So not all of them work. Essentially, the strata have to be related to each other in just a certain way. But if you have a nice stratified space, and everything we've seen has fit this model so far, if you have such a nice space, then we see that functors on the exit path category turn out to be equivalent to constructible sheaves on the space. And namely, this equivalence is given by you take your functor on the exit path category and you construct a sheaf. What is the sheaf doing to open sets? You essentially you map the exit path category of your open set into the exit path category of the whole space, apply the functor, and take a limit. It's a bit of a mouthful, but this process actually gives you a functor, which I'm calling exo, that is an equivalence of categories. There's a great example using persistence homology to talk about all this stuff. Persistence homology, if you have a sub-level set filtration of a data set, this turns out to organize as a constructible sheaf. And then we can sort of milk this equivalence and model that thing as a functor on the exit path category of the real line. But I could easily spend 10 minutes there. I'll just say, as a closing remark, there are some related ideas. We could talk about stratified covering spaces in this context, sort of maps that organize as covering spaces on strata. We could also talk about, if we wanted to upgrade this to the infinity categorical setting, we could talk about sheaves of spaces instead of sheaves of sets. And then you get the exit path infinity category is the corresponding notion. And then, like I sort of mentioned, people have upgraded this to, there's like a version of this if you're working with topoi or infinity topoi. There's a version of this if you're working with schemes. So this exodromy equivalence, where you have functors on this exit path thing being equivalent to constructible sheaves, this holds in a whole bunch of different settings. Yeah, I think that's where I want to leave it. Do we have questions?
Just one thing, because before you said, you had an equivalence of three things where you also had the coverings in there. On your last slide, you only showed me two of those.
Yes, right here, right.
No, I don't see the amount of coverings, so I wonder if you could just say a few words of what that is.
Yeah, absolutely.
So,
yeah, interestingly, when I first looked into this subject, I don't think this was an answered question. I think it was like an open question of whether or not stratified coverings were even a thing. But just like 2 years ago, I think, two mathematicians at CSU, Justin Curry and Amit Patel, Amit Patel, they wrote a great paper called The Classification of Constructible Co-sheaves that introduces this notion of a stratified covering space, and they do upgrade what I have as an equivalence of 2 categories in this presentation. They upgrade that to an equivalence of 3 categories, where you have constructible sheaves, representations of the exit path category, and then this third thing, stratified covering spaces.
Yeah, I have a question.
Yeah.
Yeah, I'm glad you mentioned co-sheaves there. So am I right? Is this subject, constructible sheaves, is this sort of all about branch covering spaces and things like that?
Yeah, ramified
It's a sort of a vague question, but anyway.
Yeah, so like ramified covers of Riemann surfaces or branch coverings, maybe more generally, they are a particular example of what may be a conically stratified space. You could sort of stratify the base of a ramified cover in terms of the branch points and the generic points. So if you stratify like that, branch coverings fit into this picture of constructible sheaves and exit path categories. But they're just an example. You could get a lot more general with how you stratify stuff and by posets.
So your thing would generalize it for what if the branch slope itself was a branch thing.
Yes, yeah.
But anyway, yeah, it's it's quite interesting that this constructible sheaves anyway is related to co-sheaves and so on. It seems like it. I don't know. I've just I don't necessarily understand it, but anyway.
Sure. And yeah, Justin Kerr and Amit Patel look at just sort of the dualized version of this, where everywhere I said sheave, they've replaced that with co-sheaves. It's just a matter of the variance of the functors, really, at a certain level. But they use, instead of exit path categories, they use entrance path categories. And so there's sort of a very natural way to dualize all this if you want to talk about co-sheaves and stuff.
Anyway, thanks.
Very nice. Any other questions?
Yeah, so Sam, if I look up stratified space, I don't anything like what you gave as the definition.
Sure. Yeah, like I said, I think
what is the that leads us to believe that this definition that you provided for us in terms of posets is, well, it's even a question, is this equivalent to other stratifications that I've heard of?
Yes, it is. I think so. There's a paper, I'm forgetting the author, but there's an expository paper that lays out 14 different things people call stratified spaces. And I believe this idea of just a continuous function to a poset generalizes most of them. There might be some notions of a stratified space that don't exactly fit this paradigm, but generally, if you talk about like a Whitney stratification or stratifying by manifolds, or a lot of these notions are generalized by this notion of a stratification.
Yeah, in particular, like a Whitney stratification being generalized by this is pretty remarkable to me, because otherwise the Whitney conditions are kind of complicated and obscure.
Yeah. So, just remind me, a Whitney stratification has like manifold pieces as strata, right?
Yeah, so let me not pretend like I know the answer. I mean, I'm sitting here in front of Wikipedia, right? I mean, like, I can read you the definition if you want.
Well, I was just gonna say, I did sweep some stuff under the rug when I said our stratifications have to be conical. Conical is a big, if you look up conically stratified spaces, you will see a definition that is, to my mind, very hard to parse. It's like, who baked this up,
Can you say what is sort of the main feature of the conical one? Because it probably, like you said, it might be lengthy, might be technical things, but is there some couple of important main ideas in there?
Totally. Imagine you have like the Earth and the Moon. As we say, you have the Earth-Moon system, and you could just call the Moon the 0 stratum and the Earth the 1 stratum. But they're not really related to each other in any way if you do that, right? Like there would be no interesting exiting paths from the 0 stratum into the 1 stratum. They're just disconnected, right? So a conical stratification wants to avoid this sort of trouble. And so what it means to be conical means where your strata meet, it basically looks like you're gluing together a copy of Euclidean space crossed with a cone on something. The something is called the link. Like I said, the definition turns out to be pretty technical, but essentially what you want to assure is that when two strata come together, they're related in that, I don't know, if you look at sort of the what am I trying to say? Where the one stratum meets the two stratum here, the zero stratum meets the one stratum, it kind of looks like a cone point.
Right. You should explain why it's called conical. That's good.
Yeah.
And
they look like cones locally.
Right.
And it has the advantage that it's well set up, if you like, for inductive arguments, because the higher dimensional pieces are put together where the strata meet by cones on lower dimensional pieces that you've already dealt with, so to speak. So you're very well set up for inductive definitions and for proving things inductively, or if you like, sheaf theoretically.
Right. And yeah, if you read, I don't know, any of the papers on this subject, my favorite, again, being this sort of expository paper by Justin Curry and Amit Patel, they do everything in terms of like, okay, well, we know the stratification is conical, so let's just talk about the cone points first. And let's talk about how those relate to, the strata that live sort of one level up. And so everything's phrased in terms of these cone points in the proofs when you really dig into it.
Sam, you don't have to remember the author of this paper with 14 different definitions of stratified paper. Do you remember the title at all?
Yeah, I can. Let me stop sharing real quick and let me pull up the reference paper that I was using because I know they've got it in there.
Anyways, I think you gave a very nice talk. Thank you. It was very understandable.
Yeah, thank you. Let me just real quick see if I can find this. I'll only look for 30 seconds or 5-10 seconds. Yeah, I don't know if I'm going to be able to find it quickly enough. So maybe I can email Nosen or.
Okay, no rush. It just sounds
with
like
a couple of references.
Fascinating talk. Anyways, any more questions? This is a very nice talk. Any questions, comments, criticisms?
Yeah, quick question. Great talk.
Thanks.
So I'm wondering if you know how nice the category of constructible sheaves is. Like
super nice.
It is really nice.
Well, what do you mean by nice? I think these things are very constructible sheaves are very easy to sort of get your hands on because they're locally constant on strata. So if you have a stratified space, you can say, well, on this strata, it's just assigning integers. On this strata, it's just assigning the empty set or something, And so from one perspective, it's really easy to write these things down. If you're wondering about like, can I take limits and co-limits?
Yeah, that's what I mean.
Is this like a topos? That's a good question. That I know those questions are addressed in the paper by Hain, Barwick, and Glasman on exodromy.
Okay, cool. Thank you.
Yeah.
Okay, if there are no more questions, let's thank the speaker again. Or no, we didn't thank you before, but anyways, thank you very much. And
thank you.
Sam, it's a pleasure. It's going to take me a little while a few hours to get it up, but I'll do it tonight. And the next time we're meeting, I think, is the 30th. Bruno, hold on, don't move. Just give me a second because his name is important. Bruno Gavaranchrovich is speaking on categorical deep learning and algebraic theory of architectures. Anyway, so that is October 30th. Anyways, ladies and gentlemen, it's been a pleasure. Thank you very much. Thank you, Sam. Thanks again. Okay, take care, everyone. Good night.
Everyone have a good night.